Hello, my name is Robert Smith, and I'm with New River Community College. And today we are looking at how to use values provided in a chemical equilibrium to solve for the change in Gibbs free energy outside of equilibrium. And we can take a look at this problem. It kind of illustrates this, where we have the interconversion between dinitrogen tetroxide, so N2O4 gas, with nitrogen dioxide, so we get 2NO2 gas. And it's provided that our K value is 0.113 at 298 K for temperature, and that the Gibbs free energy at that temperature is 5.4 kilojoules per mole. Now, the thing about it here is that we don't need this information. The only thing we needed was this. As long as this is our Gibbs free energy at standard state for this reaction, that's all we really need in order to complete this request to calculate the change in Gibbs free energy when the partial pressure of dinitrogen tetroxide and nitrogen dioxide are 0.345 and 0.221 atmospheres respectively. So to do that, we use this equation, where all we're doing is we're doing a slight modification, somewhat akin to the Nernst equation. And we have all the terms. This value, the 5.4 kilojoules per mole, that's our delta G at standard state. We know what R is. We know what T is, because T is 298 K. And now we just need to find out what Q is. And Q is going to be products over reactants. And instead of using concentrations, we're using partial pressures. So the products, as written here, are our nitrogen dioxide. So the pressure of N2O raised to the power of the coefficient, so that's squared, over the pressure of N2O4. So that's going to be 0.221 squared over 0.345. So we could just rewrite this whole equation, plugging in the values that we have. I think what we're going to do is make a small correction here. We need to evaluate this term here, this 5.40 kilojoules per mole. We need to evaluate it as either keep it in kilojoules per mole and change everything else, or change it from kilojoules to joules. And I think we're going to do the latter. We're going to change it from kilojoules to joules. So that's easy enough. 5.40 times 10 to the third joules per mole. And then we're going to add to it our 8.314 joules per mole Kelvin times 298 Kelvin times, put a little dot here, carry it to the third line, natural log of 0.221 squared over 0.345. And if you do that whole calculation, you'll find that you end up with a delta G of 556 joules per mole. So this is a non-spontaneous reaction when we change the partial pressure of the two species in equilibrium, or initially at equilibrium. So it won't go in the correct direction or the forward direction as we predicted. So what that's saying is, based on this delta G, we can expect that our whole reaction will shift to the left until it reaches equilibrium again.